All right, so the last of our series videos talking about Taylor polynomials. And remember, a Taylor polynomial is sort of a generalized version of a tangent line. And so it's going to approximate a function around a specific point, just like we always have a point of tangency. We have a point that the Taylor series is centered at. And in this case, it's sort of generically centered at what we would call A. And so that's where you see that x minus a. This is technically the Taylor series going up to infinitely many terms. This year's test is going to focus on Taylor polynomials, and so they'll never have you keep going till infinity, is my understanding. You'll be able to stop after a certain degree. And basically, we want this Taylor polynomial to match up with the original function and all its derivatives, or however many, whatever degree we specify, at that point. And so this is sort of the key feature here. This is called the Taylor polynomial coefficient. So it's the nth derivative with a plugged in divided by n factorial. That's the coefficient that goes in front of that nth degree term. And so if you want to sort of build it up from scratch, you've got a function and you've got the center. You take that center and plug it in. And so when I plug -1 in here, I get 1, and the natural log of 1 is 0. And so we've got this function that's going through the point -1, 0, and we're going to try to approximate the function as best we can there. And so now I'm just, let's say they told us to do the second degree term, or a second degree Taylor polynomial, just to keep things relatively short. I'll take the first derivative, so natural log 1 over the inside times the derivative of the inside. And then if they said second degree, let's clean this up just a little bit. So 3 over 4 plus 3x. And so the second derivative, that's like 4 plus 3x to the -1. And so that negative comes down, turns that 3 into a negative. And then I get 4 plus 3x to the -2, so squared on the bottom, and then times 3, again, right from the chain rule, because I have that 4 plus 3x being sort of my inside function. And so now I'm going to plug -1 into these derivatives, and so -1 again turns this bottom into 1, so 3 over 1 is 3. And then this again, -1 turns this into 1. 1 squared is 1. And so I just end up with -9. And so the second degree Taylor polynomial for this function would be 0. And then plus 3 over 1 factorial times x. And the center is -1, so I'm going to have x plus 1 to the first. And then minus 9 over 2 factorial times x plus 1 to the second. So this is the second degree Taylor polynomial. Let's take a look at Desmos here. And so here's my original function, natural log. And so I'm going to start typing in my Taylor polynomial that we just calculated. So y equals 0, so going through that point, and if I stop at the first degree term, I should just get the tangent line. And sure enough, that's looking good, right? Hits the curve at that point of interest, and looks like the slope is the same. Taylor polynomial just takes it that one step further, so 9 over 2 factorial x plus 1 to the second. And so now when I zoom in here, I see that I basically have a tangent parabola. So it's a parabola that's passing through that same point. It has the same slope and the same concavity, the same second derivative at that point of interest. And one thing you can do then, once you have the Taylor polynomial, is you can use the Taylor polynomial to approximate values of the function near a particular point. And so if you have this Taylor polynomial P2 and you wanted to approximate, what's going on at -0.9, you would just plug in -0.9 for x into that polynomial, and you'd have your approximation. Now, the way they are saying this is that You have your calculator available on the whole test, but it sounds like it's not really required, and so it seems like they're not going to be doing a whole lot of stuff with messy decimals and so forth, which is where this usually comes up, is when you're approximating with this, you end up dealing with some messy decimals. But who knows? That's sort of the purpose, or one of the purposes, of Taylor polynomial, is to approximate functions near that point of interest. The other type of problem, anxious off, is sometimes working backwards to find derivatives. And so suppose we've got a Taylor polynomial, and they just sort of tell you, oh, we've got this one term, this 8th degree term. And they then want you to work backwards and figure out what was the 8th derivative at the center. And the center of this Taylor polynomial is 5. And there are two ways to think about it. One way, which is sort of nice, is, well, if this is the Taylor polynomial, it has to have the same 8th derivative at 5 as this function, as the original function does at 5. And so just think about, what would the 8th derivative of this thing look like? Well, there technically would be all these other terms, but of course, if you take the 8th derivative of something of a 7th degree polynomial, those things are all just going to get wiped out. These things have more than 8 terms, or 8th degree, and so when you take the 8th derivative of those, these are still going to have x's left in them. When you plug 5 in, those parts are all going to get zeroed out. And so really, I just have to take the 8th derivative of this thing that I have written down here. What's going to happen when I take the 8th derivative? Well, the 8's going to come down, then a 7's going to come down, a 6 is going to come down. There's no chain rule stuff to mess me up. And so I'm just going to get 2.7 times all those powers coming down, which of course is just 8 factorial. And so that's what that 8th derivative must equal at 5. The other way to think about it is to go back to this general format, and we know that that term, that 8th degree term, came from the 8th derivative with 5 plugged in over 8 factorial times x minus 5 to the 8th. And so this has to match up with this. And so that means the 2.7 must have come from 8th derivative with 5 plugged in all over 8 factorial, right? Because these parts are both the same. The coefficients have to be the same. So how do I solve for that 8th derivative? Well, again, I just multiply by 8 factorial, and I end up with the same answer either way. So Taylor polynomial is sort of a fun thing that shows up lots of other places outside of Calc 2, so hopefully you enjoy working with them.